Assalamu alaikum. Dear learners, I hope you are safe and sound. This series of videos is going to cover another widely used type of sensors, that is linear displacement sensors. By the name you must have guessed that if there are linear displacement sensors, then there has to be rotary ones as well. Yes, you are right. But rotary displacement sensors are a topic of another video series which will come hopefully after this one. In this series, therefore, we are just going to talk about the linear displacement sensors. Before diving into various kind of sensors, let me clarify what displacement is for our friends who might not have a clear picture of it. A direct distance between any 2 points is called displacement. And by direct, I mean the length of a straight line joining two different points. Suppose these are the 2 points, the length of this straight line will represent the displacement between the points, whereas all other lines may represent distance because of certain constraints, but not the displacement. Let me talk about another way to understand this displacement and distance thing. I guess everyone would be familiar with at least one of the navigation apps found online nowadays. The most famous one is Google Maps. In this app, when you want to navigate from your home to, for example, your work location, the app will calculate the route and will give you the distance between the home and the work location. In this example, displacement between your home and work location will not be of any use because you are not a Superman who can fly directly towards your destination. So, if Superman was using Google Maps, then the app might have suggested a direct route from the initial location to the destination because there are no constraints for Superman, but there are, of course, many for you. Lastly, let me spell out a very straightforward definition of displacement and move forward. That is, displacement is the shortest distance between 2 points. I've mentioned it earlier that today we are going to cover only linear displacement sensors, which are also called translational displacement sensors. However, the other major category of displacement sensors, that is the rotational displacement sensors, will be left for another series of videos. So the first translational displacement sensor I'm going to discuss is perhaps the oldest device that is used to measure displacement and also perhaps the easiest and simplest one as well. I'm talking about a simple linear resistive potentiometer. A linear potentiometer uses a variable resistor, and the fact that the resistance between the sliding contact and any other terminal of the variable resistor is dependent on the position of the sliding contact. In the schematic shown over here, the resistance between the sliding contact and terminal B will decrease as the sliding contact moves towards terminal B, whereas resistance between the sliding contact and the terminal A will increase as the sliding contact moves away from the terminal A. The opposite will happen if the sliding contact is moving towards terminal A. As the resistance is changing between the sliding contact and another terminal of the variable resistor, this resistance change may be converted into a change in voltage drop if we use the variable resistors in a potentiometer form. The linearly translating object may be attached with the sliding contact of this setup, and as the object translates, the resistance between the sliding contact and another terminal of the variable resistor is going to change. That will be translated into a voltage change. This voltage change may further be used in any control system or any other suitable system that can relate the voltage change with the amount of displacement. Basically, there are three different types of variable resistors, and these types are dependent on the material using which the variable resistor have been manufactured. The first type is called a wire-wound variable resistor. By the name, you can figure out that this kind of variable resistor has a wire which is wound around a central core, and the slider can slide on top of this wire. The wire used over here is specifically called resistance wire. It shows a bit larger resistance than a normal conductor wire. As slider is sliding on the wire, the resolution of the resistance change that can be achieved using this variable resistor is limited by the diameter of the wire used. Ideally, at any particular position, this slider will be in contact with one loop of the wire, and as the slider moves forward, it will come in contact with another loop of the wire. Hence, resistance equal to the complete loop of the wire will be added or subtracted from the current resistance value. Moreover, these kind of variable resistors show low temperature coefficients so that as the temperature changes, their resistance doesn't change much. The other types of variable resistors are made out of carbon film or a conductive plastic film deposited on a central core. The slider on these kind of resistors will slide onto this deposited film, and hence you can have much more precise movements over here. Although these kind of variable resistors can be made in a much smaller size, they are less rugged because the film suffers wear and tear because of repetitive movement of the slider. The friction between the slider and the film causes the film to suffer wearing, and hence a permanent damage occurs. Friction contact between the slider and the central part of the variable resistor forces these kind of displacement sensors to have large value of resolution. A large value of resolution means the sensors cannot detect very small movement, and hence they are used to measure movements greater than 2 millimeters and up to 1 meter or so. Other problems associated with these kind of displacement sensors arise from the fact that the slider is mechanically coupled with the variable resistor, which can bounce off at high speeds. Moreover, this friction will reduce the overall life and working cycle of the variable resistors used. Lastly, one major disadvantage of using potentiometers for measuring displacement is voltage drop that will result in a waste of power. Let me try to explain this thing by drawing a simple diagram over here. Suppose that there is a variable resistor and I am deliberately making it a bit longer, and you have powered this variable resistor with a certain battery, for example like this one, and it has a voltage of 12 volts. Now if the slider is currently at this location, then you might be using these two terminals, this one and this one, to attach another device over here. It might be anything that can act as a load or any other resistance. Now if this other device has some resistance, then what is going to happen? Let's suppose you haven't attached this device right now and you have positioned this slider at the exactly center position. Then you will be getting 6 volts over here and 6 volts over here. But as soon as you attach another device, an output device or anything over here, what is going to happen? The resistance of this value, for example R load, I am going to say it, and whatever resistance is over here, let's suppose it is R2, these two resistances are going to come in parallel. And if these two resistances are going to come in parallel, what is going to happen? You must know that whenever two resistances are in parallel, the net effect is always lesser than the smaller resistance. So whatever are the values of R2 and RL, the value of the overall resistance is going to drop. If the value of the overall resistance is going to drop, then of course the voltage drop against this resistance is also going to drop. So you are not now going to get a 6 volt over here, but you might get 4.5 or anything less than 6 volts. So as soon as you apply another external thing over here, what happened? The voltage dropped. This is called loading of the system. There are certain things or there are certain techniques through which this problem can be eliminated, but that will add more number of devices into this circuit. Moving on, strain gauges although are designed to sense force or weight, but these devices measure force or weight indirectly. The primary change inside these devices is change in length of the strain gauge wire or foil. This change in length is typically in the range of few micrometers or smaller than that. Therefore, displacement in this range may be measured using strain gauges. In fact, we have already talked about such displacement sensors when we discussed diaphragm-based pressure sensors. We saw over there that The diaphragm expands because of the application of pressure, and this expansion is recorded by the strain gauge attached on the diaphragm. Therefore, strain gauges are used to measure displacements that are further used to measure something else. The main reason that the strain gauges are not directly used to measure the displacement is that they require application of force to get deformed. Hence, they will load the system if used directly. Normally, for the cases where something is showing a displacement, we don't want any measurement system to hinder that displacement. However, strain gauges will provide a considerable resistance to motion. Therefore, use of strain gauges for force or pressure measurement is much more beneficial than displacement measurement. Nonetheless, the range of sensing of displacement through strain gauges may be increased by using mechanisms like the one shown over here. The displacement of the wedge will bend the beam containing the wedge, and this bending may be recorded using strain gauges. Of course, the bending of the beam may easily be related to the displacement of the wedge. So, mechanisms like this may be used for measuring wedge displacement of up to 50 millimeters or so. A rarely used method for measurement of displacement is through the use of piezoelectric crystals. These crystals have similar issues as that of strain gauges. They require application of force to show any change in the output. Application of force will produce microscopic compression in the crystal, which in turn generate electrical charge as output. Like strain gauges, these crystals are normally used to measure force, but may be used to measure displacement in the order of micrometers or smaller than that as well. As these crystals are quite hard, the system with which they are attached has to be of high stiffness so that it can compress the crystal because of any motion. Moreover, the output generated by these crystals depends on the rate of change of displacement. So as soon as the displacement stops varying, the output vanishes. Normally, shunt capacitors are attached with these crystals to store the generated charge so that detection may be done effectively and easily. The schematic shown over here is of a displacement sensor called the nozzle flapper. What happens over here is that normally air is supplied at a known fixed pressure from this side, which flows through a fixed restriction before it reaches a variable restriction from where it exhausts. The variable restriction may be opened or closed by a flapper plate. For small range of displacement of the flapper plate, the pressure being measured in the measurement chamber is directly proportional to the displacement of the flapper plate. So as the flapper plate moves, the pressure in the measurement chamber changes. This relation is valid for small displacements only. Therefore, these devices can measure displacements in the range of 50 micrometers or so, with a resolution of 0.01 micrometer. Commonly, such devices are used to measure small displacements of the load cells because of the application of force on them. A similar sensor but utilizing light instead of pressurized air is called photonic sensor. This schematic shows the simple working of such a sensor. The displacement of the reflective plate in front of the optical fiber cables dictate the amount of light from the emitter side that will enter the detector side. Once again, these sensors are used to measure very small displacements such as those of load cells. Moving on with the discussion of sensors that can measure displacement in small range, a schematic shown over here may also be used for this purpose. The idea over here is to attach the moving body with the vane, which in turn can cover or expose the measurement photodiode to the incoming infrared radiations. Another photodiode is always fully exposed to the incoming radiations that serves as the reference photodiode. The difference between the output of both photodiodes is directly proportional to the displacement of the vane attached to the moving body. This difference is calculated by a simple circuit incorporating a comparator. For example, at a particular time, if the measurement diode is fully exposed to the infrared radiations, then the output signal would be zero, because same amount of output would be generated by both the reference and the measurement photodiodes. In case where the measurement diode is fully covered by the vane, the output would be maximum because the reference photodiode would be generating large output in contrast to minimum output from the measurement diode. Normally, such sensors are used to measure displacement in Bourdon tubes that are used to measure pressure. There are a number of instruments that can measure or approximate the displacement using ultrasonic waves or IR radiations. I won't be discussing them over here as I have already touched on these sensors in a previous video whose link is given in the description. Therefore, learners are recommended to consult that video for detailed discussion on ultrasonic and IR range sensors. There is a class of displacement sensors that cannot exactly measure the displacement but can give a binary output signifying the presence of any object in a vicinity. These displacement sensors are particularly called proximity sensors, and they are only used to sense whether a particular kind of object is present in a close vicinity of the sensor or not. Normally, there is a boundary or a range associated with proximity sensors, and if something comes inside that boundary, the proximity sensor will signal its presence. And if there is nothing in that range, the proximity sensor will signal absence of that object. Let me emphasize once more that proximity sensors will not give you the exact displacement of the object from the sensor. I'll be discussing two widely used type of proximity sensors. The first one utilizes the same working principle similar to range sensors. There is an energy source and a detector. The wave emitted by the energy source reaches the detector where a corresponding output is generated. In range sensors, the emitted energy is reflected from the object before it reaches the detector, and hence the time of flight is directly proportional to the displacement between the sensor and the object. Similarly, in proximity sensors, the energy from the emitter is reflected by the object before reaching the detector, but over here time of flight is not recorded. The only thing that is noted over here is the strength of the reflected signal. If it is greater than a certain threshold, it means the reflective object is within the sensing range. Otherwise, it is not. The most common proximity sensor of this type utilizes IR transmitter and receiver to achieve this task. However, there are different arrangements through which proximity can be sensed using IR transceiver pairs. It would take me a lot of time to discuss how infrared sensors are used for proximity sensing. But to save time and to remain on course, I would discuss only two ways through which proximity can be sensed. In the first way, intensity of infrared reaching the receiver will decide whether there is something in proximity of the sensor or not. This thing can be achieved in turn in two different ways, which I will explain in a bit. Another way is to use a modulated infrared instead of a simple one. Same kind of setups can be established with modulated infrareds as that of simple infrared. But a major advantage that is achieved using modulated infrared is its insensitivity to environmental light or infrared radiations present around the environment. So the first form in which a simple infrared radiation transmitter and receiver are used comes in two different settings. The first one is called a through-beam sensor, in which transmitter is placed on one side whereas the receiver is placed on the other side. The infrared radiations emitted by the transmitter are directly received by the receiver, but if there is something in between the transmitter and the receiver, it will block these radiations. Hence, a low output of the receiver will mean that there is something present between the transmitter and the receiver. You must have experienced this kind of sensing when you place the retail items which you have purchased on the conveyor for the checkout process in some supermarket. As the object moves on the conveyor, it reaches the end of the conveyor near the cashier. A through-beam IR sensor is intercepted by that object, and hence the conveyor automatically stops. The other form in which you can find these kind of proximity sensors is called a reflective form. In this case, IR radiations are emitted by the emitter, which are reflected by a reflective surface, and if that reflective surface is close enough to the transmitter-receiver pair, the reflected radiations are high enough to cause the output change in the receiver. As the reflective object moves away from the transmitter-receiver pair, the amount of radiations that are reflected drops, and hence the receiver cannot receive a certain minimum threshold of reflected IR radiations. Usually IR radiations are used in these kind of sensors. However, you can choose any electromagnetic radiations to perform a similar function. But there are different problems associated with different electromagnetic radiations. For example, radio waves and microwaves will pass through the object and will be reflected slightly from most of the objects, and hence it would be difficult for the receiver to detect the reflection. However, if you move beyond the IR radiations, you will come across the visible light, and you should be able to understand it easily that why visible light cannot be used in this setup. As visible light is present all around us, it can easily distort the visible light coming out of the transmitter. Moving beyond the visible light, you will come across the ultraviolet and higher frequency electromagnetic waves, which become hazardous for our health. Therefore, these are not used over here. So we are left with IR radiations and have to manage things using these radiations only. These kind of sensors are extensively used for line following and wall tracking tasks. Moreover, optical encoders, which are rotational displacement sensors that I'll discuss in my next lecture, utilizes through beam type of IR transmitter receiver pair. Some major drawbacks of using IR radiations are the interference from ambient light, dependency on the reflectivity of the object, and dependency of the output on the distance between the sensor and the object. On the contrary, we can use a modulated IR radiation that can easily tackle the issue of noise being induced from the ambient light. IR radiations at a high frequency are generated by the emitter, and if the same frequency is received by the receiver, then it means there is something that is reflecting the radiations towards the receiver. Or if you are using a through beam setup, it would mean that there is nothing present between the transmitter and the receiver. The high frequency IR radiations are generated by flashing the IR transmitter on and off. This makes the IR radiations emitted by the transmitter less susceptible to distortions induced by the ambient light and issues of low reflectivity of the objects. These kind of sensors are mostly used in IR remotes, which are used to control TVs, audio systems, or any other device commonly found in our homes. Apart from using electromagnetic radiations or specifically IR radiations, there are other ways to form proximity sensors. Two most commonly used proximity sensors in any industry are based on change in inductance or capacitance because of the proximity of any object. Inductive proximity sensors change their inductance whenever some metallic object is present in the vicinity, whereas capacitive sensors are more suitable for non-metallic objects. These kind of proximity sensors doesn't emit any radiations and hence doesn't have any transmitter or receiver pair. In fact, what is happening over here is that in case of inductive proximity sensors, the presence of metallic object near the sensor changes the magnetic inductance of the environment, which is detected by a suitable electronic circuit. On the contrary, in the capacitive proximity sensor, the presence of any non-metallic object near the sensor changes the dielectric properties, which in turn changes the capacitance of the capacitor inside these proximity sensors. This change in capacitance is read by the attached electronic circuitry and hence the output is generated. I have deliberately left two displacement sensors for separate videos as they require special attention. Therefore, it is recommended that you guys view the next two videos talking about LVDTs and laser interferometers before you can make sense of the discussion related to sensor selection. The main thing dictating the selection of the displacement sensor is the magnitude of the displacement that needs to be measured. However, the environment where the sensor is to be used is also important as far as the selection process is concerned. Therefore, displacements greater than 5 meter can only be measured using range sensors which utilize ultrasonic waves or electromagnetic waves of higher wavelength, whereas for measurements in the range of 2 millimeter to 2 meter, potentiometers, LVDTs, variable inductance and capacitance transducers may be used to sense displacement or proximity. However, if you move below the range of 2 millimeter, then range of sensors including LVDT, strain gauges, optical sensors, laser interferometers, and some others may be used. All these sensors are quite sensitive and have high resolutions, which allow them to measure such small displacements that can be in order of micro, even nanometers or less than that. If we specifically talk about displacement sensing in harsh, corrosive environments, then sensors that can easily be shielded and protected against such environments may be used over here. Sensors like LVDT, variable inductance and capacitance sensors are quite easy to be protected using a sheath or a cover, making them suitable for use in harsh environments. So, dear learners, I guess I have adequately covered a range of linear displacement sensors in this and the referenced videos on LVDT and interferometers. I've tried to cover the basic working principles of these sensors and hopes that viewers have developed a reasonable understanding about the overall working. That's all from my side. Thank you and take care.